My name is Andrew. I'm a lecturer in epidemiology at the Disease Dynamics Unit of the Department of Veterinary Medicine at the University of Cambridge. So I use mathematics and in particular mathematical models to try and understand better how infectious diseases spread through populations and how we might control them better. I work on many different species, including in particular human diseases. I'm particularly interested in childhood infectious diseases. Most of my projects, though, involve working with large teams from very different disciplines, including vets, medics, microbiologists, and perhaps most importantly, policymakers from governments around the world. In my work, I try to apply my modelling to questions which are actually important and practical in order to provide useful advice on how to better control disease within populations. Most recently, I was involved in data collection on a larger scale when my old boss, Professor Julia Gog, asked me to help with a BBC documentary on the spread of pandemic infections. The TV programme was intended to commemorate the 100th anniversary of the 1918 influenza pandemic and to give a sense to people of what it was like to live during a pandemic. The other important aspect of the programme, though, was to collect data on human contacts and mobility that could be used to help us to control the next pandemic, which at the time of recording, we find ourselves battling. So the data has become incredibly useful a lot faster than we ever thought when we made the documentary. So mobility data sets like this are basically just a big matrix or a table of values of the number of people who move between two different places, what we call an origin-destination matrix. We use statistical models to pull out the general patterns from this data to try and understand how the rates of movement depend on the structure of populations. So this is important partly just to simplify down and tease out the patterns in our data to understand them better, but also it allows us to make predictions to other populations and use the data more efficiently within models of transmission. So the most popular models we have to understand human mobility are so-called gravity models that capture the two most important rules that govern human movements. The gravity model predicts the number of people moving between two locations, an origin and a destination, as a function of the distance between them and the size of the local populations. People are more likely to travel to a local population than a remote one, so the probability of moving between two places, the parameter rho, measuring how quickly this probability falls with distance. People are also more likely to travel from a small population to a large population, which is reflected in the powers, tau, on the population sizes. Now, you can probably see the resemblance to Newton's law of gravitation that I'm sure you've learned about in physics class, but the gravity models were actually developed in the social sciences rather than having a link to physics. One of the big reasons this form of model is so popular is not because of a deep link to the physics of gravity, but because if you remember your log rules and you apply a log transform to this, you can actually turn the gravity model into a simple straight line, which can then be fitted using a standard regression model, so just a standard straight line fit. So we're using the gravity models that we've estimated from our mobility dataset from the pandemic documentary to predict what the patterns of movements across the country are and how that links to transmission. So we do this essentially by integrating this simple model of human mobility into a model that describes the dynamics of how disease transmits, and that's a story for another time. But once we've done that, we can make predictions for how quickly a new infection could spread and what the relative risk of infection is in different parts of the country. So this is an example map that I've made where I seeded an infection in a small town called Hazelmere, just outside of London. This is the town that we used for the pandemic documentary. So this map, this is the sort of output that we would prepare and share with government agencies, and shows the time of arrival or the predicted time of arrival for the first case in different areas of the UK. So the colour indicates how quickly the disease arrives, and it also illustrates the speed of the spatial spread. So for this simulation, it only took 15 weeks to cover the whole country. Not actually untypical of what we would expect for a pandemic disease, and fairly consistent with what we saw in the UK. In fact, the spread was probably even faster because there were multiple introductions in different parts of the country. But from the map, we can also see how the patterns of human mobility have impacted on transmission. For example, there's a relatively early arrival of the disease in high population density areas, and the low density, more remote areas are relatively more protected.